In this webinar, I'd like to really try and talk about Docker and its use for the embedded developer. So this is building on experience we have here in Feabhas. We've been using Docker for a few years now, and the work we've done in consultancy with a number of our clients over the years associated with it. I'm sure you all know who Feabhas are. Otherwise you probably wouldn't be here, but obviously we specialise in training consultancy for the embedded development area, embedded software area. So in terms of those objectives, as I mentioned, we're really, what I'm trying to do, sorry, I apologise first, I've got a slight cold as well, is the main focus here is looking at software quality and saying, how can we use software quality to improve, use Docker containers to improve software quality. The intent is not to actually show you how to build your own containers. That has been covered quite extensively in a number of blog articles that have been posted on blog.feabhas.com. But I will talk briefly as we go through the presentation about this area of building your own containers. So without further ado, the main audience, the assumptions I'm making for the main audience here is that we're working in C and C++, typically for the deeply embedded systems. I will talk about embedded in terms of things like Cortex-A and Linux later, but really my emphasis here is where we're probably dealing with a microcontroller, obviously predominantly ARM, Cortex-M certainly dominates this market. One other thing is the use of the build system. Now, a lot of us over the last couple of decades have got very used to using integrated development environments such as Kyle or IAR, where the build is sort of hidden from us. We hit an F5 or we select a build from the menu and some magic happens in the background and we get an ELF file and a binary file we can reflash our targets with. So part of this need going forward is to take back control of the build system. Particularly in the background, there is GNU Make. That's still the general build system that most C and C++ systems use. And they may have layers on top of that, such as CMake. We internally actually use something called scons, and I'll touch on scons later just as an example of how that works with our container models and how we use it. But the same basic principles apply to this. In terms of the outline, brief coverage of what Docker is, try and put that in as simply as possible of some of the terminology used around Docker and containers. But most importantly is trying to address and look at how, when using Docker and container technology, how it can massively improve basic software quality very easily and very cheaply. And there's three areas we can apply the Docker model. On the desktop, so those doing their everyday development and typically doing your local compilation on your machine and building a system and possibly even debugging using local hardware connected, say, over USB and JTAG. Most importantly is the modern and more agile model of trying to build proper build and continuous integration pipelines. So I'll explain that and show how Docker is central to most modern build systems and makes this transition from desktop to build very, very simple. And finally, I'll come back to for Docker deployment, that if we wanted to try and actually launch applications and use Docker, where we are today in terms of being able to use it. So the two key terminologies we need to be aware of when we're using Docker is this concept of container. Now, Docker isn't the only container technology out there. It came out of the Linux world. It's been around for probably a good decade now in terms of the concepts, and actually dates much further back. And for the first number of years, Docker and container technology was very limited to, well, not very, but limited to Linux type systems. But that has really changed in the last couple of years with greater support for both Windows and Mac. Most importantly, we also have this concept of a container image. Now, in terms of, if you go to the official Docker website, so this is docker.com, they term a container image. So a Docker container image is a lightweight, standalone executable package of software that includes everything needed to run an application, code, runtime, system tools, system libraries, and settings. So what this is a mechanism where we can define and wrap up an application with all of its dependencies. That's very important. So any external libraries it's needing. So normally if you have to install an application on your laptop, for example, quite often you may need to add some other technology or some of the libraries to support that. So it could even be things like, you know, Java runtimes or Python runtimes for some of the tools that are out there. So what Docker allows us to do, and very important is the keyword lightweight there, it allows us to take an application and wrap it up and make sure that everything it requires is part of that image. So on a machine that supports container technology, it doesn't need any of those particular things installing apart from the ability to run Docker. And that's the key aspect of here, is that it gives us the capability now to run applications on any machine without actually having to do any form of installation apart from the Docker runtime. So we talk about taking an image and then running that image, and that can be done, for example, from the command line, or it can be automated through build servers. So a typical Docker run, we may have some sort of command line window, a terminal window open, and we can invoke Docker run. You have a number of various options. We'll see a couple of those later, and we give it an image name. And at that point, what it will do then is spin up that application. It will create effectively a process. But very important, this process is sandboxed from your underlying system. So if I'm running it locally on my laptop, then this application I'm running can't see my underlying file system unless I explicitly enable parts of that. So you have the concept of Docker volumes, where I can choose to take some of my file system, typically it's my source files, my C and C++ files, and be able to pass those into the container. And it can work on those, and those volumes can either be read-only or read-write, as an example. So it's very nice in the fact that I can have a degree of security in the fact that this container can't access other parts of my application. Other files I may add, I may supply, if there needs to be certain licensing files or particular files outside of my normal source files, they can also be mounted as well and made available, where you might have a bit of software that itself requires some sort of license to run it. So today, where can we run Docker? So this is Docker container technology. So most of Linux and Unix, as you can guess, is pretty well served by Docker. Underlying that, you do need a machine that if you're running, for example, an Intel architecture, that supports things like the hypervisor technology, so something called Hyper-V. So older machines possibly wouldn't be able to run Docker. You probably need more recent, last couple of years, you probably want a machine that has that sort of hypervisor in hardware technology. The big changes came a couple of years back is when there was native support for both Windows and OS X on the desktop. But quite significantly from a build server perspective is Windows Server 2016, Microsoft have very much embraced Docker technology as well. So this means if you have servers and anything to 2016 or later now can also natively run Docker as well. So that was quite a significant step forward in terms of the adoption and the use of Docker. So what is an image? Take, for example, here, this is an official image. So I'll talk a bit about official and unofficial images. So GCC is the GNU compiler collection. So this is quite well known as one of the open source C and C++ compilers. And this allows us to compile C to different language standards and have different characteristics. This is the default sort of desktop one. This would normally create an application to run, for example, on a Linux system or a Windows system or a Mac system. So with an image also has a set of tags. So tags is sort of a versioning model, and that normally reflects the underlying technology. So here we have GCC support a number of different versions of the GCC compiler. So we have GCC 5.5 up till the very latest 8.2. So 8.2 is really at the leading edge of that. And each of these are separate images, and means that each of these can create a separate container associated with that. And typically on the website, which is called Docker Hub, it'll explain how to use a particular image. So one of the first benefits you see from container technology is the fact we can take a common set of source files and we can very easily compile them against differing versions of the same compiler or different compilers. So here we're using two versions of GCC. And this allows you to look at the migration policies, etc. We can ensure very quickly. And you don't have to go through what can be quite tricky effort of trying to co-reside two versions of the same tool. Anybody knows you try to install, most laptops only like one version of a particular tool installed, and typically the latest version. So it can be quite difficult to have, for example, two versions of a compiler and being able to easily swap between them. And the benefit of the container technology is we don't need to do that. We don't actually even install our compilers. We just, again, have to have Docker container technology available to us, and we can just run the image against the images, and that can create this environment that has the compiler and all of its dependencies enclosed within that container, and we can pass our source files to it, and it will go through the process of building that source file and checking that they're going to compile correctly and ultimately run as well in those environments. Where do our images come from? There is something called Docker Hub. Docker Hub is where all the official images exist, and these are typically all free and openly available. And they're a massive mixture of types of images. We tend to work with things like the GCCs, for example. There are images to do with operating systems, but more typically there are images to do with particular applications. There's a lot around web technology. If you want to try a particular web technology, again, you can spin up a Docker image and try those sorts of ideas. But here we're very much focused on the embedded space. If there isn't an official repository made typically by the manufacturer or the owner of that particular software application, then it is very easy to build your own Docker files. So there's a process. You create this concept called a Docker file, and then using Docker technology, you actually build the image file itself. So the benefit of the image file is it can be managed locally. So it can just be locally on your laptop, for example. It can be hosted within a company intranet, so anybody within the company can see it. Or it can be pushed back up to something like Docker Hub. They're similar to many things like GitHub, where it can have public and private management of repositories, so that Docker file can be shared within known groups, as an example. And the one benefit of going through a Docker file is we're guaranteeing that everybody is working to that same image, is working to exactly the same set of dependencies within our particular system. So I won't spend detail on this, but here's an example of a Docker file. This is sort of what comes out of the blog article to explain how we get to this point. But this is one we use internally. So for a lot of our cross-builds, a lot of training courses, we're using on Cortex-M as our target boards. And this is installing the GCC ARM cross-compiler. Now, this happens to be the 2008 GCC 7 version Q2 update. And of course, there are later ones as well. We also internally use a build system called Scons. Scons itself is sort of replacement for Make and CMake. That technology happens to be built on top of Python. So our particular container image we build we start with a base image. Now this we're using a variant of Linux called Alpine. Reason for using that, it's incredibly small. It's only a few megs. And it has the glib library, which is required by the compiler itself. The compiler, of course, is a C application. We add to that Python 2.7 for scons. We add the scons, and that is done, if anybody's worked with Linux would know the typical way of adding packages. And then we add the compiler to it. And in this case, we're actually pulling the compiler compressed image from our local file system rather than from the web, but we could do either. Once that image is built, it's now available, and we can run that and then add our C and C++ application code, our projects, to that, and know that anybody using this image is guaranteed to get exactly the same results with exactly the same set of software. So there's no variation in any of the libraries or any of those dependencies, which has been a major benefit to improving the quality of what we're doing, where people have got different machines with potentially slightly different builds and different path dependencies set in them. So this isolates all of that, because in effect you've got a clean environment you're always starting from. One of the questions sometimes people, and I certainly did when I first came across container technologies, how does it compare to the concept of hypervisors? So hypervisor technology has been around for many years, and it's normally used where you can host another operating system on a host operating system. So for example, Oracle have a tool called VirtualBox. VirtualBox is quite widely used, especially in Windows. So VirtualBox allows you, for example, to run a Linux complete operating system within the within the Windows environment. So you run up the hypervisor, you run up the virtual machine, and then you have a full complete operating system to work on. So the difference is that with a container technology, rather than being operating system centric, it's application centric. So when you're building a container image, it's really for an application. It's less about the underlying operating system. Because obviously certain applications happily run on both Windows and Mac and Linux. So the idea here is we eliminate that and we just build around that particular application with its dependencies. There's still a place for hypervisors. If you're doing work around kernel code, you're working at that level where you need knowledge, and you might be doing things that are very dependent on the application, on the operating system. So there could be stuff to do with, for example, the different threading models you get across Linux and Windows. Then there's still a place for hypervisor, and they happily can coexist within that particular model. So hopefully that gives you a sort of appreciation of what a container technology is. So in terms of using it, if we first focus on Docker on the desktop, so like I say, the big change that happened a couple of years back was the native support on both Windows and OS X for Docker. Now on Windows, you have to be running Windows 10. So sorry, I imagine most people out there are probably still on Windows 7. We see the majority still on Windows 7. It needs Windows 10 technology and this Hyper-V technology as well. And it's probably one of the major compelling reasons to look at Windows 10. They actually have another feature on Windows called Windows Subsystem for Linux that is a similar technology that allows you to run, for example, a bash shell within Windows 10. That's different to Docker, but it gives you some overlap between the two. So my perspective, I'm actually running on a Mac, and having Docker availability at the desktop on Mac has really made this very seamless. And of course, most Linux applications will natively support the ability to run Docker within that. So the intent here is I can have the same image. So I'll take our GCC example I was speaking about, and I can run that same image as a container on all of those platforms, and I will guarantee to get exactly the same results with exactly the same software out of them. So now it doesn't matter what my underlying operating system with. I can ensure that people on a team or people across projects or people across companies are guaranteed to get exactly the same results. So it's a repeatability of being able to do a certain amount of work within our system. Now, one thing it does if you're not Linux centric, if you're not working on the Linux desktop, but I'd say the majority of embedded programmers still are, I'd say Windows certainly dominates that space, is it immediately opens up some very nice, useful open source software. So much of traditional open source software, a lot of free open source software is pretty much assuming you're working on a Linux platform and using GCC. So it can be very difficult to get certain applications running on a non-Linux environment. Even with OS X, with Mac, that is a Unix platform, some of them are still tricky. You have to build from source, and even that, as you can, never always works as you'd expect. So a couple of examples we use quite heavily. Top left is a tool called Lizard. Lizard is a nice tool. It allows you to collect something called cyclomatic complexity. So this is one of the standard metrics, especially in C applications, that's been used for many, many years. And certain standards, so you take ISO 26262 as an example in the automotive industry, one of the requirements is something called low complexity. So how do you assess low complexity? Well, cyclomatic complexity is probably one of the best metrics we have out. It's not, it's not perfect, it's not foolproof, but it's a good tool. Now, you may have commercial tools doing that already, and that's great. And I hope you do have those sorts of tools already doing that. But for those smaller businesses or those that just haven't at the moment, then it means you can immediately start collecting that sort of metric, again, without having to go through the process of trying to install Lizard as a tool on your local system. Bottom left, Seedling. Seedling is a lovely environment. If you're moving to more of an agile mindset, your company wants to become more agile. It supports the concept of test-driven development, TDD. So Seedling is very centered on C rather than the C++. And it's a nice framework where it has all the dependencies to go through a TDD cycle where you do your tests, you do your build, and it manages all of that. But it, again, pretty much assumes you're going to be on a Linux GCC type model. So by having a Linux container, we can apply those ideas even though we don't have that locally on our machine. Top right is Clang. Clang, if you're not familiar with it, is a modern build system, C compiler system used for Clang itself is a C language front end built on top of a technology called LLVM. And that's used by many modern languages. So you may have heard of things like Rust or Swift or Kotlin, some of these languages used in mobile phone technology or development technology. The Clang is the front end one. It's basically source code compatible with GCC in that. But one of the benefits of Clang has as well, and you can compile Clang to, for example, Cortex-M series as well. It has some Clang utilities, and a couple of really useful utilities there are called Clang Tidy and Clang Format, One we use heavily internally is one called Clang Format. What this allows us to do is it does auto layout of source code. So the idea is anybody in the company can write the code as they like. Where do the curly brackets go? We don't sort of care. But then we run it through Clang Format, and it has a meta file that says this is where the curly brackets are going to sit. This is the alignment. This is the spacing. This is the layout. And that means we get a conformity of source code. That means that anybody coming to source code, we basically have this principle, and again, it's an agile principle, that by looking at the code, you shouldn't necessarily know who's written it. And this happens before we commit it to the code base as such. And then there are other useful tools. So C++ check is one. There's one called OCLint. And these give you some fairly basic but quite useful static analysis on the code base. And again, you may have commercial tools, the QACs and the LDRAs, and that's great if you've got those. But again, if you haven't, these tools make it very easy because, again, they're all free. They're all available. There's no cost as a model to start using these tools today in your particular environment. So here's an example if I was running Lizard on my desktop. So I've got Docker run, which is spinning up a container. We start off, the idea with containers, you can keep containers so you can continue to work in them, or you can run them once and discard them after you've finished with them. So the RM is saying, once I've collected the metrics, I don't need this container again. I can spin it up again if I really wanted to. The important thing is -v. This gives us this volume model. So that's now allowing to take me part of my file system. So here we've got the present working directory. So whatever folder I'm in, whatever directory I'm in, I'm now sharing that to the container. So I'm mapping that through. So it basically sees just that directory structure and nothing above it. So it can't get above that directory structure. You have to have a place in the container where it gets mapped to. So here it's /user/project. And then we have our image name. So this happens to be one we've built. So I've built Feabhas/alpine lizard. This is a very small image that gives us lizard. They can have version control on them. So again, we have repeatability if we stick to a version number. And also you can default to something called latest. Latest will just go and pick the latest one up that might have been updated. And then finally, here's the command. The command can be automated. Here we've got lizard. The -c says set a boundary, a cyclomatic complexity of an upper bound of 20, for those that know what cyclomatic complexity is. And that will give me a report of all the files, all the functions, an individual metric for all of those, and then give me the base metrics across the project from that. But I get that locally, so I can see that. I can again get that file back locally rather than living within the container itself, should I want to. So incredibly easy to use, and I could run that same line on Mac, Windows, and Linux as well, and get the same output from that particular one without having to install Lizard. So one of these side benefits, of course, is it means that if we have a set of support utilities, a set of support tools, then we can guarantee that everybody in the particular team is using exactly the same build model. There's no machine-specific dependencies. The fact that sort of Joe's got these sort of dependencies on their machine that happen to affect the build. It could be a path setup. It could be some other tool they've installed over the years that is causing a particular build maybe to pass that then fails for somebody else within the system. And it means we can get a consistency of layout, consistency of rules regarding what we define as a team is our own internal quality metric. So easily allows you to start setting those gates that we would do just to improve our basic intrinsic quality. And also a lot of this can be done without having to involve IT support. I mean, IT support in many organizations, first is they don't tend to understand anything but Windows. So they won't allow you to have Linux or Linux tools on a system. And also getting anything done can take sometimes days to turn something around. So by getting Docker installed, it means because it's sandbox and it's safe, then it means we can securely and safely run a number of these tools without having to go through that painful process of getting admin rights to do installation, but also not having to every day keep going back to the IT support group saying, please, can you do this for me? Please, can you do that for me? So it brings those straight away, can bring those benefits to us, which I always think is fairly attractive on many organizations. So looking at what we can do, one of the problems we always hit is for code bases that, most code bases exist for many, many years. And the problem is legacy support that we have is being able to guarantee to recreate a particular image. So in many companies, I'm sure you've probably got them laying around. You've got some old PC running Windows 98 or something with a particular version of a particular compiler, and only that machine can recreate that particular image if we get a bug reported in the field. So by starting down this route to move towards compiler technology, especially where individual containers can be versioned, then we can start to say, well, we can guarantee to recreate that build, but without having to have a particular machine that's just set aside with those particular operating system characteristics in it, because that's built already into that particular container at the time. So even the containers can have the versions of, for example, different underlying operating systems. They can say that container its base image is that particular version of that particular operating system. So there's obviously a limit to how far we can go back today, because obviously container technology has only been around in the last number of years. But it does mean we can start setting a precedence going forward that the sooner we adopt container technology, the sooner we can start to worry less about this need to do a certain amount of legacy support from a build perspective. We can guarantee this sandboxing, rebuild, clean room environment for rebuild technology. The other thing we're seeing a number of companies now is with the evolution of languages. Now C is moving slower than C++. We had C99, C11, which we've seen almost zero adoption of so far, and we have C20X coming along as well. Where in the C++ community, there's been a much greater acceleration of the language. It started really with C++11, and then there was 14, 17, and now 20 is pretty much ratified. And we have a number of customers who are going through that painful process of trying to move a legacy code base written pre-C11, modern C++, into using later compilers. Because sometimes you hit a problem where there may be a particular bug and the vendor would just say, well, it's not supported. We're not going to fix it on that particular version of the compiler. Your only solution is to upgrade to a later version of the compiler. So this gives us a way of actually being able to, very simply with having a different container for each version of the language, with different compiler versions, is we can start trying different flags, for things like what is going to be effect of different optimization models, and safely do that and repeatedly do that, again, without going through that process of trying to have all these variants on a single machine or a single build system. So it allows us to explore and experiment much simpler than it would be traditionally associated with that. The other thing, of course, is that we want to, newer laptops, newer systems, newer operating systems. It means that we start to get, as we see today, many people are naturally reticent moving from, say, Windows 7 to Windows 10. Every time there's a new version of an operating system, that choice is, do I want to move to that latest operating system version because I've got these set of tools and they may not be supported, or they may not work very well, or there may be problems moving to a later version, a newer, cleaner environment. Obviously, the benefit of Docker technology, so for example, recently, if anybody knows Macs, the Macs have gone through a major update of their operating system. But because Docker was supported prior to that update, then there's no effect on all of the tools I was using, moving from the old version of the Mac OS to the newer version of the Mac OS. And we have some machines still on the older version, and we get the same output because it's the Docker technology that's managing that, not the underlying machine. And obviously for that, we're relying on Docker and the people building Docker to keep Docker relevant for the particular systems we're working on, and having a certain amount of backward compatibility with those in our system. Now, one thing Docker's probably not suited to so well is where you have applications. So remember, the principle of container is we're wrapping up an application with its dependencies, is an application that's very GUI centric. So very natural GUI centric. So it's using either windowing GUI graphical system, or it's using the Mac or the Linux graphical system. You can do it. There's a concept called X11 forwarding. You can do that on Windows. You can do it on the Mac as well, that allow you to have visibility of those tools locally through that. But it's, to be honest, I've done it and it's not great. It's a little bit clunky. It works really well with tools that offer a web-based interface, for example. Because you have this ability within a Docker container to map from internal ports to native ports, local host ports on your machine. So you can fire up a web browser and then see into the container through the web interface. So, because obviously a lot of modern systems use a web-based interface for a certain amount of configuration. That is absolutely fine within container technology, but it's where if I was using an IDE, say I was trying to use a particular Eclipse as an example, not I love Eclipse, but say we were trying to use Eclipse as a Java-based windowing system for doing an IDE. That you can do, and I have done, but it gets to a point saying there is no real benefit to doing that. Either you move back to hypervisor technology, you run a full operating system in your operating system to give you that tool, which I have to do. For example, on the Mac, I run something called Parallels that gives me Windows 10 or Windows 7, so I can run a particular UML tool called Enterprise Architect, because that's not supported outside of Windows in that. So that's sort of the idea we've got to work with, that certain things work well. One thing containers can do, which is quite nice, is the ability to pass devices to them. So if you've got something like a JTAG connected to a USB port, that again can be mapped into the container. You can make that device available to your container, so it can, again, we can still use that particular model within our object system. So my normal way of working is that I'm using a local editor on my machine. So my favorite is Sublime Text. I'll be editing my text in that environment, but when I want to build, I invoke the build through Docker. So I've got that consistency of builds. And again, with the editor, I can choose either to run with the debugger, I can use either local or remote debugger, depending on the model I want to choose within that, but typically a local debugger at that. So that hopefully gives you some idea of how we use it on the desktop, using it day-to-day, and some of those benefits. Probably the most significant benefit moving forward, and where the greatest benefits tend to be for a company in terms of, we talk about return on investment, putting the time and effort in to put Docker in, is when it comes to build systems and moving towards a modern, and especially for those companies that are looking to think about more of an agile approach to the build system. So continuous integration, and again, I apologize, I can't remember where I stole this from, but I thought this sort of summed it up very well. It says continuous integration doesn't get rid of bugs, but it does make them dramatically easier to find and remove. So I'm a big advocate of trying to find the bugs early, use static analysis, use a lot of code reviews, put a lot of emphasis to try and stop the bugs getting in there in the first place. But that, it's like a Swiss cheese. There's only certain ones we're going to find. So CI, putting the effort into CI forces you to address the quality model much, much earlier than we would typically do. And also means you have to take a certain amount of ownership of that. It's not just somebody else's responsibility. So the classic model is where we have a build server, we're going through a certain amount of integration, we're putting together different parts of the software, and suddenly the build is failing. So the main build server goes through and tries to do the linking and integration model, it's just falling over. And yet you go back to the developers and they're saying, well, it works absolutely fine on my machine. I can't understand why it's not working for you and why it's not building for you. So we've got a couple of goals when we come to build and continuous integration. So our main one, and of course what Docker immediately offers, is that if we're using a container technology, then both developers and the continuous integration environments, the build servers, are guaranteed to be working using exactly the same container runs from the same container images, from the same Docker images. So there's there is an impossibility in a sense to have this, it builds on the laptop and it doesn't build on the server. We've never had that position in that particular case with the system, because all of those dependencies are wrapped and sandboxed in the container. So we've got to be using the same thing within that. And it has this knock-on effect to do with testing. So we have this benefit because it's a clean room each time. Each Docker container, when it's spun up, is a complete clean environment, and we just pass through it the files we want. Then if we've got a series of different tests, we've got unit tests, integration tests, system tests, then we're assuring there's sort of no pollution from one set of tests to the other. So we ensure that a previous test is not causing a later test to pass. And also, of course, we might have a system where people are building locally on a Windows system, but actually the build server might, for example, be running Linux. So that can, of course, there can be different stability in different models within there that, again, it builds locally, it runs absolutely fine, but as soon as we put it on the build server, it's failing the build associated with that. In terms of build server technologies, this has moved on rapidly, and in the last couple of years, it's moved on so many leaps and bounds. All modern build technology utilizes Docker. So if you go to any modern build server, then Docker is an available and inherent part of doing a build within that. The two main technologies used within a company boundary, where people have local build servers, is the well-known one called Jenkins, free and open source. We actually have a Jenkins server here. The other one from Atlassian is one called Bamboo. We used to run Bamboo. We moved over to Jenkins internally for that. But both those are very common build servers. You've got some sort of server sitting in the back room, and that's running your builds. On the other area that's grown hugely is software as a service, so cloud-based support. And there's a whole raft of tools out there, build server models out there that can run either by the actual company, or we can even run them through things like AWS. AppVeyor is one people use a lot because it's very geared up to doing Windows-centric builds in many senses. But of course, because we're embedded, we're not so focused on building applications that run on a Windows platform or a OS X platform and a Windows platform. You may have heard of Travis. Travis has very high integration with things like Git and GitHub. We actually also use Atlassian Bitbucket. We use Bitbucket in two ways. One, it's our main repository for all of our courses and all of our code, but actually they've built into Atlassian now many of the features from Bamboo. So we can actually do a build within the cloud when we commit software. That build automatically happens again as part of the commit. So we have a local and remote builds associated with those. So there's many different ones out there, and they have slightly different cost models to do with private and public builds or the amount of time you spend building, etc. But are really simple, but they all work on exactly the same principle. And that principle is typically called pipelines. And the way modern pipelines work is that they're just a set of steps we go through the build, but with container technology, it changes. So now, for example, take our local Jenkins server. When we commit a change, so we've made a change to the software. Now, again, we happen to use Git. I know a lot of people are still sort of stuck on Subversion. Git is an easier model, but it works happily with Subversion as well. Then we commit to the cloud, so we're using private repositories under Bitbucket. Jenkins detects those changes and then will automatically pull down a fresh image. So we'll clone that repository from the cloud to a local, what's called Docker volume. So it creates this concept of a sandboxed file system, for a better sense, and puts all of our application code on that. As part of the build, then it will be tagged to a particular image. So it looks at the image and says, okay, you want the ARM GCC cross build. And it will see whether it's got it cached locally. If it hasn't got it cached locally, then it will go out to, we store ours on Docker Hub. These are open again, and it will go and find the latest image off Docker Hub, pull that image down, and then spin up a container, mounting the code volume into the container. And that's now a complete clean environment to do the build, and we can see whether that build will pass or fail based on everything we've got associated with it. So it's the repeatability of the build is absolutely key. And like I say, normally we've done that build locally on the desktop, so we have every confidence that it's going to build. So sort of an anomaly we found where we weren't always following the procedures. Again, like we're human, sometimes you bypass these ideas. I can run GCC locally on the Mac, but actually that's running Clang, the C language compiler. And weirdly, there are some subtle differences between GCC and Clang to do with things like header includes. Clang by default isn't case sensitive, where GCC is. So we had some weird builds where it was building locally, but because I hadn't done the due diligence of doing a proper Docker build locally, then I was pushing it up and it was failing on the build server, which was really, I should have been dealing with that before, but it was caught straight away. And then once you have a build server, the idea is you can build a build pipeline, a continuous build, continuous test pipeline. And each of those pipelines, the key thing about the pipelines is each step in the pipeline has its own unique Docker container. So this has the real benefit to a build server is that we don't have to install all of our different tools on one build server. So all these different compilers, all these different test tools, all the runners we're running, they don't have to all try and coexist at the same time. So your build server as a minimum only needs Docker. And that once it's got Docker installed, you don't actually have to add So once you've got Jenkins installed and you've got Docker supported with Jenkins, that's all you need. You don't have to install any other software. The other benefit of the Docker model is that you can then share artifacts from one step in a build to the next. So for example, in the build stage, the output of that would normally be our out file and our binary file, the thing we're going to flash the target with. So that can then be stored. We can throw away the rest of the container. We don't need to keep that around, but just keep the output, the artifacts. So those particular files, the alpha and the bin file, and they then can become the input volume to another container. So we have a particular set of integration tests we run, and that means they run against that particular image that has been the output. And then they can be run against our system tests using simulation technology and our hardware tests as all the steps. Now, this particular technology we're using here is a sort of, I'm sitting on top of Jenkins, and it's called Blue Ocean. Jenkins used to be quite difficult, I've thought to configure, and that's why we used to use Bamboo. But Blue Ocean has made this very, very simple. And the actual graphic, ignoring the containers and the artifact bit, is actually taken directly from the visualization from Blue Ocean. It's actually a snap of the web page visualization you get when you're doing the build. And you see the green ticks or the red crosses if a build fails. The benefit now is we have in our build server is we can set up these different pipelines for the different types of build we want. So we have the concept of branches. So we have the master branch, which is typically the one that's being used for a given course. We have development where we're doing course updates. So that may be to do with language issues or just typo fixes, bug fixes within the code. And sometimes we do feature branches. They're typically where we might be doing a customer specific course and we want to spin the things out into that particular branch. The aim is that each branch can have its own build with its own set of Docker containers. So for example, on the development branch, we would typically do our static analysis and our metrics test and our basic unit testing, but we wouldn't normally do those on the master branch because we assume that they will have already been done as part of the development branch, because that gets merged back in to our master branch that becomes our releases associated with it. As an example here, an interesting bug we found with our current source code. So a particular library we're using, we are moving from GCC 5.4 to GCC, actually ultimately 8, 7.2 was here. And this is really to support the latest versions of C++, so 17, for the embedded. So this is ARM Cortex-M series running C++ 17. We found a particular library in there that had changed from GCC 5.4 to 7.2 and was actually causing our build to fail. But we could find this by running the same source code against our GCC 7 container, and again could track down very quickly where that fault was. And basically it's a macro. A macro has been removed, so it's not expanding properly during the preprocessor directive. So that was made it really easy without again having to have two different compilers installed side by side on the same machine to do this. Probably the thing that gets most freaky is it's a little bit like the film Inception. You can run something called Docker in Docker, and we actually do this locally. So Docker in Docker means that I can have a machine running Docker, and then I can spin up a free standard official Docker image called the Jenkins Blue Ocean. So the company Jenkins, they put it out, they're called Jenkins CI Blue Ocean. So this is a full installation of the Jenkins build server, but running within a Docker image, and you have volume mount to it. In that, I can then set up the build stages, as I've just shown you, and each of those build stages are still using a Docker image, a Docker container to run their steps. So this is again referred to as Docker in Docker. So this means your actual build server only needs Docker installed. It doesn't need any other software tools to install it to start building this. The other real side effect or benefit of this is you can actually have a full build server on your desktop. So actually also run this Jenkins Blue Ocean as a Docker in Docker on my actual Mac. So I have a full build pipeline that I can test and run and experiment with on my local machine without actually needing to use one of our main servers to try things out and test certain ideas as we're going through. But like I say, it is a little bit freaky and a little bit sort of mind-bending is what's actually going on here. But it's the same basic principle associated with it. So to finish off is what about Docker for deployment? What about using Docker if we're building end customer applications we want to put out in the field? And the short answer is, if I'm Cortex-M and I'm using a real-time operating system like FreeRTOS or ThreadX or Nucleus, etc., we cannot build a image and container that runs that type of code. Major reasons being is some of the underlying required technology, hypervisor technology, and that sort of chip, the Cortex-M, just doesn't have that sort of technology yet. Now, it'll be interesting down the line that obviously originally was on the Cortex-A series, has hypervisor technology. That's been introduced to some of the Cortex-R series on the V8 architectures, and it will be interesting to look ahead of whether there will ultimately be some form of hypervisor technology in the microcontroller world in the future. But for the moment, no, you can't do that. That's just not a model that works within the Docker model. So we can use Docker for our builds and for our tests, but not actually on real hardware within that. What we're using as a sort of a hardware house, and this has been a major improvement for us, is to use some simulation technology. So about a year ago, we started working with a company called Jumper, and they have some very cool technology that runs in Docker. And this is a simulation of Cortex-M, and it simulates to the chip level, not just to the core. So they've got things like the STMs. We happen to use the STM-F4s on some of our courses, but also the Nordic chips like the NRF52s. And what this allows you to do is take your actual binary image, so there's artifact output from the build, and actually run them in the Jumper Docker simulation. So this is allowing you to test an embedded executable in running instruction set execution of the Cortex-M. But the real benefit we've seen with the Jumper model is it maps right out to even things like the GPIO or I2C or SPI. So we can inject events. So it has this wrapper you can use. You can use a Python model, Python scripts to inject events, so interrupts, button presses, etc., to force inputs and read the outputs and test the outputs as part of this build script. So now we can run up a test script where we're saying, here's an image. When it comes up, this should be the setting, the GPIO configuration we expect in terms of highs and lows. This should be the messages over the particular bus we're using. And then with this input on this particular, then we should expect this model to happen, and trace them through and do short runs and longer runs to start doing a true system level boundary test. The other nice thing we found about Docker is it's extensible. You can write your own peripherals. So a particular temperature sensor that I'm using, then you can define your own, using a C++ framework, your own model of those temperature sensors and how they're connected to the particular pins on your system. And even things like Bluetooth and Wi-Fi can be mapped through to your underlying machine as well. So this is the nearest we're getting at the moment to give us that missing step between host-based tests, where we're just still using standard host-based compilers, and true target hardware tests without actually needing real hardware in the loop. So it gives us a high degree of confidence before we start putting this code on the target. Finally, if you happen to be running on something like a Cortex-A system, so good old Raspberry Pis are a great example of these, that all the modern Cortex-A support hypervisor technology, and you're running Linux as an example, there are a couple of companies that have done some really interesting work. The main leading one is Balena. You might have heard of them. I'd certainly used them. I've been working with about 18 months from a company called Resin, resin.io. So they've recently renamed themselves. And these have a technology where you can deploy Docker to a running system. So it supports, because one of the benefits of Docker container, this is generally referred to as microservices, is you can spin up a Docker container in the field. So you can have a running platform sitting there with this container technology and remotely bring up a container and take down containers. And Balena have this idea. They have a web-based platform where you can see your running application and you can do software upgrades over the air through build. They do all the build of the image and actually deploy the container to that particular, and you have access to the underlying hardware on things like the Raspberry Pi. But they support a number of different platforms, and there is a model for building your own particular image. So again, if you're running on a Cortex-A, you're running things like embedded Linux. It's a very, very interesting technology, and they've expanded it recently to support a broader model. And interesting, this model is actually very highly used in general purpose Docker. So Docker on the cloud, many companies are actually using Docker for deployment. I say this term microservices, so the Amazons, etc., they all use Docker as a deployment model now because it has this real benefit of being able to take an application down and bring it back up again in a very seamless model, or bring in a new version alongside an older version and very quickly swap between the two. Another company out there, the HipRiot, they do some other slightly differing technology that allow you to build container technology for Cortex, typically for like the Raspberry Pis again, for Cortex-A. So of course, if you're running Intel, then of course it tends to be more easily supported. So for example, one of our customers is running, one thing Docker does have is a kit that allows you to define your own base image. So if you've got a particular variant of Linux, so these guys happen to be using Wind River Linux as their distribution, they built a complete Wind River Linux distribution and could run their end application code on that to do all their testing before they deployed it to the real hardware that again was running the Wind River Linux. So they could do a true test of their application using a Docker-based container that completely simulated all of their hardware, including their graphical interface. The device had a touch panel and graphic interface for that model as well. So that's that's a very, very cool technology, but you have to be on a Cortex-A or an Intel type architecture in that. So to finish up, we've been working with Docker for a couple of years now. Internally, we've seen massive improvements in many of our quality aspects. And probably the biggest change has been the build server, being able to easily take ownership of the build, not relying on a build expert, because you don't have this complex configuration of the build server. Because everything is running in Docker containers, then there's no dependency within the build server. So it's very trivial to set up that continuous integration pipeline. And it's the next series of blogs I'll be putting out is actually about doing that and using Docker to help you do an embedded build to generate a target-based system. On the desktop, I say we've seen benefits of bringing in many of these very useful open source tools that allow us to just improve static analysis, just improve certain metrics, and make it easy and trivial to do that and have it as a standard part of all of our builds now. And the deployment, we've been playing with the deployment, said we tend to focus on the Cortex-M systems, and we do obviously have the Linux training and a lot of customers working with Linux. And as example, one of the systems I was running was sitting in my house, a Raspberry Pi, and I happened to be sitting out in Singapore and could actually do an update to the code base and send that and see all of the update and actually log into it. It supports things like SSH, so secure shell, over that to securely log into the system, which again was quite mind-blowing to be able to sit many thousands of miles away and actually do all of that particular model. So we can see where that is going and the changes to our system. But across the board, they all can help improve intrinsic quality because they force you to be consistent and think about the way you're developing software and the build model. And once it's set up, it is painless and trivial and very, very simple. Actually, something I should have mentioned, one of the bigger differences between Docker and hypervisors is the speed to spin up a container. So in Docker, it typically takes a couple of seconds. So on our build servers, each step typically is taking a couple of seconds. Where with hypervisor technology, you may have heard of something called Vagrant. They can take a couple of minutes to spin up the actual operating system to run the application as such. So that makes a massive difference, especially if you're paying per build time, which you do typically with software as a service with that particular model. So where next? If you go to labs.playwithdocker.com, there's some really nice stuff there where you can try and get a feel for Docker and try some ideas. Obviously, most of those are geared around doing stuff in the web. So it shows it how very easy to set up a web server and start doing things like Node.js or JavaScript type stuff. So, and again, I find that really useful as somebody who's not an expert in that field, but having to learn because of good old IoT and having to become more familiar with many of those aspects around web servers and RESTful architectures. It allows me to start trying those ideas and actually spinning up simple web servers on my desktop using Docker to try out things like MQTT. So very, very easy for those ideas. In terms of building your own image, there's a series of articles on blog.feabhas.com that takes you through building your own particular image and how the tools are required and how to make that image smaller and more compact within that. And finally, if you look in Docker Hub, you'll see there's all the official images, such as the Jenkins one I mentioned, but also there's community ones as well. So we have a Docker Hub, you'll find there's a Feabhas area, and under that there are all the images we use. So the cross builds with GCC, the lizard I mentioned, CPP check, etc. They're all on there as well to freely be used. And it's a good place to build your own and put your own up there as well and make available to the rest of the community, because half the time you think, well, I'd like to have this, and somebody has already done it. Made it very easy available. So for example, this morning we were asked a question whether Bamboo can run in a Docker container like Jenkins can, and the answer is yes, it can, because Atlassian have an official Docker image for Bamboo already defined on Docker Hub within that. In terms of how it fits into what we do and why are we interested in this technology, then of course Agile has really moved on in the last couple of years, and we've been working heavily looking at Agile for the last 4 or 5 years. And it's my keen interest. So we have a number of courses where we're talking about what does Agile real mean, and build servers and Docker has been a major part of those. So for example, you can see TDD for embedded C using Seedling, and it gives us a framework for saying you can try and do these things without having to go through installing all of these tools associated with it. So thank you for attending. I hope that's proved useful.